Greetings, my dear listeners. Today we begin a new journey, this time toward the stars, the planets, and the very question that has perhaps fascinated humanity more than any other: are we alone in the universe? We will be speaking about the Drake equation, the famous formula that attempts to estimate the number of intelligent civilizations in our galaxy. This equation was proposed by astronomer Frank Drake in 1961. He did not intend to provide a final answer. His goal was to create a framework for discussion, a way to organize the questions we must ask in order to approach the mystery. And therein lies its power. The equation became not so much a number as a conversation, a bridge between science and philosophy. The Drake equation appears simple. It is a product of factors, each representing a stage on the path to civilization. First we ask, how many stars are born in our galaxy each year? Then, what fraction of those stars have planets? Of those, how many planets may be habitable? On how many does life actually arise? On how many of those does life become intelligent? And finally, how many civilizations endure long enough for us to detect them? Each factor is not just a number, it is a story, a scientific and philosophical challenge. When Frank Drake first wrote down his formula, he admitted that many of the parameters were unknown, but the structure of the equation itself allowed scientists to focus on seeking answers. Philosophically, the Drake equation is a mirror. It reflects not only our knowledge but our hopes, our doubts, our longing to understand humanity's place in the cosmos. When we ask, how many civilizations exist, we are really asking, who are we? Are we unique? Or are we part of something greater? The story of the equation's origin is equally compelling. In 1961, a conference was held at the Green Bank Observatory in the United States. Scientists gathered to discuss the possibility of searching for extraterrestrial signals. It was there that Frank Drake presented his formula. It instantly became a symbol of a new science, the search for extraterrestrial intelligence, SETI. More than half a century has passed since, yet the equation continues to inspire researchers and dreamers alike. Think of it. Each star in the night sky could be home to planets. Some of those planets may resemble Earth. Perhaps at this very moment, somewhere far away, beings exist who ponder the same questions as we do. But how can we find them? How can we estimate their number? The Drake equation becomes our guide in this quest. In this first chapter, we have only opened the door. In the chapters to come, we will examine each parameter of the equation step by step. We will speak of stars and planets, of the origin of life and of intelligence, of the fate of civilizations and their ability to endure. And of course, we will reflect on what all this means for us, the inhabitants of a small planet on the edge of the Milky Way. We have opened the door to the mysterious world of the Drake equation, and now it is time to take the first step inside. The first factor of the equation is the rate of star formation in our galaxy. How many new stars are born in the Milky Way each year? This question seems simple, yet behind it lie many cosmic secrets. Stars are the foundation of everything. Without them, there would be no planets, no life, and no us. Each star is a kind of factory, where chemical elements are forged. In stellar cores, carbon, oxygen, iron are created, the building blocks of planets and of life itself. Thus, when estimating the probability of civilizations, we must begin with the question, how many such factories are set into motion within our galaxy? Scientists estimate that on average 1 to 3 new stars are born in the Milky Way each year. This is modest compared to the early universe, where star formation was far more active. But given that our galaxy is over 13 billion years old, the total number of stars is estimated at about 400 billion. And this is only one galaxy. Philosophically, we may say that every new star is a chance for new worlds, new stories, perhaps even new civilizations. When we gaze at the night sky, we do not just see light traveling from the past. We see the universe's endless experiment, where at every moment the possibility of life is born anew. The history of studying star formation is deeply tied to the advances of 20th and 21st century astronomy. With infrared telescopes, astronomers learned to peer into dense clouds of gas and dust where stars emerge. They discovered that the birth of a star is dramatic. Clouds collapse, rotate, form a protostar, and around it appears a disk from which planets may one day arise. Think of it. Somewhere right now in our galaxy, a new star is being born. Perhaps planets are already forming around it. Perhaps on one of those planets, billions of years from now, life will arise. Or perhaps intelligent beings already gaze at us, counting their own Drake equations, asking the very same questions. Thus, the first factor of the equation, the rate of star birth, reminds us that the cosmos never stands still. It constantly creates, renews, and evolves. Every new light in the sky is another step on the path to the great question: how many civilizations might exist alongside us? In the next chapter, we will discuss the second factor of the equation: what fraction of stars are surrounded by planets? For it is planets that become the stage upon which life may appear. In the second chapter, we spoke of stars and their birth. Now it is time to move to the second factor of the Drake equation, the fraction of stars that have planets. For it is planets that become the stage for life, the scenes upon which the drama of evolution and intelligence may unfold. For a long time, scientists did not know whether other stars had planets. We assumed they must, but there was no direct evidence. That changed in the late 20th century. In 1995, astronomers Michel Mayor and Didier Queloz announced the discovery of the first exoplanet around a sun-like star. That discovery marked the dawn of a new era. Today, we know thousands of exoplanets, and the number keeps growing. The methods of exoplanet discovery are remarkable in their ingenuity. One of the most widely used is the transit method. When a planet passes in front of its star, the star's light dims slightly. Telescopes such as Kepler and TESS detect these tiny dips in brightness, allowing us to discover planets even at vast distances. Another method is radial velocity. The star wobbles slightly under the gravity of its planet, and this motion can be measured through spectroscopy. Today it has become clear. Planets are the rule, not the exception. Almost every star has at least one planet. Many have entire systems, sometimes more complex than our own. This has transformed our understanding of the cosmos. Once we thought the solar system was unique. Now we know it is but one among billions. Philosophically, this discovery profoundly alters our view of the universe. Once Earth was thought to be the center of all things. Then we learned it was only one planet orbiting the sun. Then we discovered the sun was only one among billions of stars. And now we know that planets are as numerous as stars. We move ever farther from the idea of uniqueness and closer to the realization that life may be widespread. The history of exoplanet research is full of drama. The first discoveries were met with skepticism. The existence of planets around other stars seemed too extraordinary, but year by year the evidence grew. Today, the discovery of an exoplanet is almost routine. Scientists are even beginning to map the atmospheres of distant worlds, searching for signs that might indicate life. Think of it. If nearly every star has planets, then our galaxy contains hundreds of billions of them. Among that multitude, there must be worlds like Earth, and if life arose here, why not elsewhere? The second factor of the Drake equation assures us the stages for the drama of life are everywhere. The question is, how many of them truly become inhabited? In the next chapter, we will turn to the third step of the equation. How many planets may be suitable homes for life? In the previous chapter, we spoke of planets as the stages upon which the drama of life might unfold. Now it is time to move to the next step of the Drake equation. What fraction of those planets are truly habitable? For not every planet becomes a home for the living. When astronomers speak of a habitable planet, they usually mean the habitable zone, the region around a star where temperatures allow liquid water to exist. Water is a universal solvent, the foundation of biochemistry as we know it on Earth. If liquid water can persist on a planet's surface, life akin to ours might arise. But the habitable zone is no guarantee. A planet may orbit at the right distance from its star yet have too thin an atmosphere to retain heat, or conversely too thick, turning its surface into a furnace like Venus. Life requires a delicate balance of many factors: temperature, atmospheric pressure, magnetic field, chemical composition. Modern studies suggest that potentially habitable planets may be abundant in our galaxy. The Kepler Space Telescope has found dozens of candidates that resemble Earth in size and orbit. Scientists estimate there may be tens of billions of such worlds in the Milky Way alone. Think of it, tens of billions of chances for life. Philosophically, this is profoundly inspiring. We live on a planet that seems unique, yet it may be only one among many. Earth is not the exception, but part of a grand cosmic multitude. That means life itself may not be rare, but commonplace. Then the question, are we alone, becomes, where is everyone else? The study of habitable zones is tied closely to Earth's own story. Our planet was not always so hospitable. Its climate shifted, catastrophes occurred, yet life endured and adapted. This reminds us that even within the habitable zone, a planet's path may be complex and dramatic. Scientists are beginning to broaden the concept of habitability. Could life exist in subsurface oceans beneath icy shells like Europa at Jupiter or Enceladus at Saturn? Could it arise under entirely different chemical conditions? The Drake equation does not confine us to Earth's template. It invites us to ask questions and to seek answers. Think of it. Somewhere in our galaxy there may be a planet very much like Earth. Oceans may roar, forests may flourish, living creatures may breathe. Or perhaps there are worlds utterly unlike ours yet filled with life. We do not yet know, but the very possibility enlarges our imagination. Thus, the third factor of the equation reminds us, the stages for life are set, but only some become suitable theaters, and it is those we must seek. In the next chapter, we will turn to the most mysterious step. How often does life actually arise on such planets? In the previous chapter, we spoke of planets that may be suitable for life, but the mere possibility of water and the right temperature does not mean that life will actually arise. The next factor of the Drake equation poses one of the most difficult questions. What is the probability that life truly emerges on a habitable planet? Here we step into territory where science knows very little. On Earth, life appeared relatively quickly, within a few 100 million years after its formation. This suggests the process may be natural and inevitable when conditions are right. Yet without a second example of life, we cannot be certain. Scientists explore the origin of life in many directions. Some study the chemical reactions that may have taken place in the primordial ocean. The Miller-Urey experiments of the 1950s showed that simple organic molecules can arise from a mixture of gases under electrical discharges. Others search for traces of life on Mars or in the subsurface oceans of moons like Europa and Enceladus. Still others propose that life may have come to Earth from space, the panspermia hypothesis. Philosophically, this question touches the very essence of life. Is it an accident, a unique confluence of circumstances? Or is it a law woven into the fabric of the cosmos? If life arises easily, then the universe is teeming with living worlds. If it is rare, then perhaps we are truly alone. The history of science here is filled with passion and doubt. Every new experiment brings clues, but not yet final answers. The discovery of extraterrestrials, organisms living in boiling springs, acidic lakes, deep ocean vents, showed that life can be far more resilient and varied than we imagined. This broadens our view of where life might begin. Think of it. If life appeared on Earth so swiftly, perhaps it arises everywhere water, energy, and chemistry combine. Perhaps billions of worlds in our galaxy already harbor biospheres. But there is another possibility. Maybe Earth's conditions were unique and life here is the exception. In that case, our planet is a true miracle. In any case, the very fact that life exists on Earth proves that the universe is capable of producing the living. That alone is astonishing. But to know how often it happens, we must find a second Earth, or at least evidence of life on nearby planets and moons. Thus, the fourth factor of the Drake equation confronts us with the greatest mystery. How does life arise? And while we seek the answer, the search itself inspires, for it forces us to look deeper into who we are. In the next chapter, we will speak of the next step. How often does life become intelligent? For simple life may be widespread, but intelligence is a different story. In the previous chapter, we reflected on the greatest mystery, the origin of life. But even if life arises, the next step is not obvious. How often does it become intelligent? This is the fifth factor of the Drake equation, and perhaps the most enigmatic of them all. On Earth, life existed for billions of years before intelligence appeared. The first microbes arose more than 3.5 billion years ago. But intelligent beings, humans, appeared only a few 100,000 years ago, a mere instant compared to life's history. Should we see intelligence as an inevitable result of evolution, or as an accident tied to special circumstances? Scientists still debate this. Some argue that evolution tends toward complexity, that intelligence was destined to emerge. Others claim intelligence is just one possible path, not a necessity. Earth hosts millions of species, yet only one created civilization. This gives pause. The history of science shows the road to intelligence is winding. Dinosaurs ruled the planet for tens of millions of years but never built technology. Their extinction opened the way for mammals, and eventually humans. Without the chance event of an asteroid impact, intelligent life might never have arisen. Or its bearers might have been creatures utterly unlike us. Philosophically, this touches our sense of uniqueness. We like to see intelligence as the pinnacle of evolution. But could it be just one of many possible outcomes? If life across the universe often remains microbial, then we are a rare exception, a special spark in the dark. Yet there is another perspective. Perhaps intelligence is an evolutionary advantage. It allows a species to adapt faster than genes alone permit. We can build tools, alter environments, cooperate. Then one may suppose that on other worlds, too, beings capable of thought and culture will arise. The stories of anthropology and biology intertwine here. We study human origins, traces of ancient civilizations, and animal behavior. Apes, dolphins, crows, all show elements of intelligence. Perhaps intelligence is not an exception but a spectrum. And in the cosmos, this spectrum could be rich in forms. Think of it. On some distant planet, beings may already have endured their own paleontological accidents, their catastrophes and triumphs. Perhaps they too gaze at the sky and ask questions as we do. Or perhaps life there has remained at the microbial stage, never taking the leap to intelligence. Thus, the fifth factor of the Drake equation reminds us, intelligence is not a given but a mystery. We do not know if it is inevitable or rare, but the very fact it exists on Earth already makes us witnesses to something extraordinary. In the next chapter, we will ask what happens next. If intelligence emerges, how often does it develop into a technological civilization capable of communicating across the stars? In the previous chapter, we discussed the enigma of intelligence, how often life becomes intelligent. But even if intelligence arises, it does not guarantee the development of a technological civilization. The sixth factor of the Drake equation concerns precisely this: how often intelligent beings build culture, science, technology, and begin to reach out to the cosmos. On Earth, Homo sapiens has existed for tens of thousands of years, yet only in the last few centuries have we truly become a technological civilization. The telescope was invented only in the 17th century. Radio emerged in the 19th. The first signals we sent to space were in the 20th century. This is a vanishingly small moment compared with the whole history of humanity, let alone of life on Earth. One might ask, is the leap from intelligence to technology inevitable? Perhaps many civilizations remain at what we would call a pre-cultural level. Beings may possess minds yet never build machines, never study the stars. On Earth, dolphins and elephants show high intelligence, yet they do not construct radio telescopes. Perhaps the universe abounds in such intelligent but non-technological worlds. On the other hand, technology grants immense advantages. It enables control of environments, survival in harsh conditions, protection from catastrophe. Thus, one may argue that if intelligence exists, technological development is only a matter of time. Carl Sagan believed this, suggesting that any sufficiently intelligent civilization will eventually reach for the stars. The history of science on Earth shows that technological leaps can be rapid. In just a few centuries, we went from steam engines to spacecraft and computers. The process was fraught with crises, wars, dangers, yet it was unstoppable. This gives hope that other civilizations may follow similar paths. Philosophically, the question is this: is civilization a law of development or an exception? If it is a law, the universe should be full of signals. If it is an exception, we may be alone among billions of stars. Think of it. Somewhere distant there may be beings who already built their radio telescopes and computers. Perhaps they are searching for us just as we search for them. Or perhaps they live in harmony with nature, having chosen to forego technology. Then we would never hear them, even if they are nearer than we think. Thus, the sixth factor of the Drake equation reminds us, intelligence does not guarantee civilization, but if civilization arises, it transforms not only its planet but the universe itself, entering into dialogue with the cosmos. In the next chapter, we will turn to the final factor of the equation, the longevity of civilizations, for even if they arise, the question is, how long do they last? In the previous chapter, we reached the sixth factor of the Drake equation, the rise of technological civilizations. Now it is time to consider the final and perhaps most important factor, how long such civilizations endure. This parameter largely determines the outcome of the equation. Even if civilizations arise often, their short lifespans could explain our silence in the universe. On Earth, human civilization in its technological form has existed for only a few centuries. We have been transmitting radio signals for barely 100 years. This is a vanishingly brief moment on cosmic scales. If civilizations tend toward self-destruction, through wars, ecological collapse, or other crises, their chances of encountering one another are extremely small. Carl Sagan once said, "The longevity of civilizations is the greatest unknown factor." He understood that the answer to the ultimate question, "Are we alone?" depends on it. If the average lifetime of a civilization is 1,000 years, the galaxy may host thousands of neighbors. If it is only 100 years, then we are almost certainly alone. Earth's history gives us grounds for both hope and worry. We see humanity grappling with challenges, from climate change to the threat of nuclear war. Yet we also see our capacity for cooperation, for building science and art, for overcoming crises. Perhaps it is culture and knowledge that allow civilizations to endure. Philosophically, this factor forces us to think of our own future. What will make our civilization sustainable? What values and choices will help us avoid self-destruction? For when we ask how many civilizations exist, we are also asking, how much time do we ourselves have? Some scientists suggest imagining possible paths of development. Some civilizations may destroy themselves, never leaving their home planet. Others may learn to manage resources and become long-lived. Still others may reach levels where they begin colonizing space. The question is, into which category will we and our possible neighbors fall? Think of it. Somewhere in the galaxy there may be a civilization millions of years old. Their technology and culture may be beyond our comprehension. Perhaps they are already observing us, or perhaps most civilizations perish long before they can establish contact. Then the silence of the universe becomes understandable. Thus, the final factor of the Drake equation reminds us, the fate of civilizations depends not only on stars and planets, but on the civilizations themselves. We determine how long we will live and what marks we will leave in the cosmos. In the next chapter, we will begin to draw conclusions. We will try to bring all the factors together and see what numbers the Drake equation yields and what those numbers mean for us. We have reached the point where we can put all the factors of the Drake equation together. It is like assembling a puzzle. The separate pieces, star formation, planetary systems, habitable zones, the probability of life and intelligence, the longevity of civilizations, now begin to form a picture. But what does that picture look like? When Frank Drake first presented his equation in 1961, he inserted rough values. His estimates suggested that our galaxy might host anywhere from 1,000 to 100 million civilizations. The range seems enormous, but it reflects how much was unknown. Today we have more data. We know that almost every star has planets. We know that there may be billions of potentially habitable worlds. We understand that life arose quickly on Earth, suggesting the probability of its emergence may be high. Yet the questions of intelligence and longevity remain unresolved. Thus, modern estimates also vary widely, from dozens of civilizations to millions. Philosophically, the equation is like a mirror reflecting not only science but our hopes and fears. Optimists plug in high values and declare, the galaxy is full of neighbors. Pessimists use low values and insist, we are almost certainly alone. Yet in both cases, the equation serves as a way of framing the right questions. The history of science shows that even rough estimates can inspire. In the 1960s, the first attempts to search for extraterrestrial signals began. Astronomers pointed radio telescopes at the sky and listened. They knew the chances were slim, yet the very idea of the search became a powerful scientific and cultural catalyst. Even the absence of signals became meaningful, forcing us to ask, perhaps there are fewer civilizations than we imagine. Think of it. If the Drake equation gives us a range, from dozens to millions of civilizations, then either way we are confronted with cosmic grandeur. If there are many, we live in a galaxy filled with intelligence. If there are few, then we are especially precious as the only known civilization. Thus, the Drake equation, taken as a whole, does not provide a final answer. It only sketches the boundaries of the possible. And therein lies its power. It turns the abstract question, are we alone, into a concrete set of problems to investigate. In the next chapter, we will discuss the famous Fermi paradox, the question that asks, if the universe is full of civilizations, where is everybody? In the previous chapter, we combined all the factors of the Drake equation and arrived at a wide range of possible values. Yet as soon as we imagine millions of civilizations in our galaxy, we encounter the famous Fermi paradox. Its essence is simple and astonishing. If there are so many civilizations, where are they? Why do we not see any traces? Enrico Fermi posed this question in 1950 during lunch with colleagues. He reasoned, the Milky Way is ancient. Its stars are billions, its planets even more. Even if only a small fraction are suitable for life, civilizations should be plentiful. Then they should already have explored the galaxy, left signals, bases, traces. But we observe nothing. Where is everybody? Asked Fermi, and that question became one of the deepest in astronomy and philosophy. There are many attempts to explain the Fermi paradox. Some argue civilizations are rare and we are the exception. Others say they exist but are too distant or communicate in ways we do not understand. Still others suggest civilizations are short-lived, dying before they can meet one another. Bolder hypotheses abound. Perhaps civilizations exist but deliberately avoid contact, the so-called zoo hypothesis. Or they are so advanced that we simply cannot recognize their presence. Or maybe we live in a simulation, and the number of civilizations is determined not by natural laws, but by the rules of the game. Philosophically, the Fermi paradox places us before a mirror. We question not only others but ourselves. If civilizations tend toward self-destruction, are we fated for the same? If the universe is full of life yet unseen, does that mean we are searching in the wrong way? The history of the search for extraterrestrial signals is bound to this paradox. Since the mid-20th century, SETI projects have scanned the sky for radio transmissions, but so far the cosmos remains silent. That silence may be temporary, but it has already become part of our experience, part of humanity's cultural image. Think of it. Perhaps the answer to Fermi's question lies right before us. Maybe we are too young as a civilization to hear others. Maybe neighbors exist, but wait until we mature. Or perhaps we truly are unique. In any case, the paradox drives us to think more deeply and to search more persistently. Thus, the Fermi paradox does not invalidate the Drake equation but complements it. It reminds us that science is not only numbers but also questions that open new horizons. In the next chapter, we will speak of what kinds of signals we might expect from other civilizations and how to search for them. In the previous chapter, we spoke of the Fermi paradox and the silence of the cosmos. But if we assume civilizations do exist, the next question arises: what signals might we expect from them, and how should we search? This topic is closely tied to SETI projects and to humanity's boldest dreams. When people first thought seriously about extraterrestrial civilizations, it seemed natural to imagine the signal would be radio. Radio was our dominant means of communication in the 20th century, and scientists assumed other intelligences might use it too. Thus began projects to search for narrowband radio signals that could stand out against cosmic noise. The first experiments took place in the 1960s. One was called Project Ozma. Astronomer Frank Drake pointed a radio telescope at two sun-like stars and listened, hoping to catch artificial transmissions. Nothing was found, but the idea itself launched a new field of science. Since then, technology has advanced tremendously. Today's radio telescopes can scan millions of frequencies at once. Ideas have emerged to search not only for radio, but also for optical flashes, powerful laser pulses that might serve as interstellar beacons. Some scientists even suggest advanced civilizations could employ neutrinos or gravitational waves to communicate. Philosophically, the question of signals is tied to the question of ourselves. What would we send into the cosmos to represent our civilization? Music, mathematics, paintings, prime numbers? In 1977, the Voyager spacecraft carried the Golden Record, a disk containing sounds and images of Earth. It was a gesture of hope, a symbolic greeting to the universe. The history of science is full of dramatic episodes. In 1977, a radio telescope in Ohio recorded a strong, narrow-band signal, later dubbed the WOW signal. Its source has never been explained. To this day, it remains a mystery, a reminder that the search can yield surprises. Think of it. If civilizations do exist, perhaps signals have already reached us, but we did not know how to recognize them. Perhaps we are looking in the wrong places, or for the wrong things. Perhaps future technology will reveal what is now hidden. Thus, the 11th chapter of the Drake equation story brings us to a practical dimension. The search for signals is not mere dreaming, but real scientific work. It demands patience, imagination, and faith that somewhere out there is someone who is also listening. In the next chapter, we will discuss the other side of the coin. Should we ourselves send signals into space? And what risks and hopes does that carry? In the previous chapter, we spoke of searching for signals from other civilizations, but there is another side to this question. Should we ourselves send messages into space? This issue provokes heated debates among scientists and philosophers. for it concerns not only science but the safety of all humanity. The idea of actively transmitting is known as METI, messaging to extraterrestrial intelligence. The first attempts came in the 1970s. In 1974, the Arecibo radio telescope sent a message toward the Hercules cluster, composed by Frank Drake and Carl Sagan. It included simple diagrams, the structure of DNA, an image of a human, the solar system, and the telescope itself. It was symbolic. The signal was far too weak to be realistically received, but it marked a milestone. Humanity had announced itself. Since then, several initiatives have followed. Some scientists believe we must say hello to the cosmos, for silence will bring no answers. Others warn, we do not know who might hear. What if the civilization that detects our message is hostile? The dilemma resembles a fable. Should a traveler call out in a dark forest, not knowing who may respond? Philosophically, METI raises questions about our self-image. How do we wish to appear to the universe? What should represent humanity? Scientific data, music, art? Or is a simple mathematical signal enough? These debates reflect not only science but culture, our identity. The history of cosmic messages is steeped in symbolism. The golden record aboard the Voyagers was more than an experiment. It was an act of faith. We sent Bach and Chuck Berry, greetings in dozens of languages, the sound of the sea, and a child's laugh. Together they formed a portrait of Earth, crafted for possible cosmic neighbors. Think of it. We live in an age when we can leave a mark on the universe. Our signals may travel for millions of years, and even if the civilization that receives them arises millennia later, it will know of us. There is something moving and inspiring in this. Yet the question remains, should we do this deliberately and on a large scale, or is it wiser to listen first and speak later? These questions remain unanswered, but they make the Drake equation all the more alive and philosophical. Thus, the 12th chapter of our journey opens the field of responsibility. In thinking of civilizations in the cosmos, we inevitably think of ourselves, who we are, and what we wish to leave behind. In the next chapter, we will discuss the cultural and philosophical impact of the Drake equation, for it is not only a scientific formula, but an idea that has reshaped our view of the universe. In the previous chapter, we reflected on the messages humanity has sent into space. Now it is time to speak of the cultural and philosophical impact of the Drake equation itself. For it is not merely a mathematical formula. It is a symbol of our thirst for knowledge and our desire to understand our place in the cosmos. Since its creation in 1961, the Drake equation has become part of both scientific and popular culture. It appears in books, films, lectures, and articles. It is discussed not only by astrophysicists, but also by philosophers, writers, and artists. The equation has become a metaphor for the search, not only for other civilizations, but for the meaning of human existence. Philosophically, the equation opens several horizons. The first is the horizon of humility. Our place in the universe may be far less unique than we imagined. The second is the horizon of hope. If civilizations abound, then we may have neighbors, perhaps even friends. The third is the horizon of responsibility. If we are alone, then it is our duty to preserve and develop intelligence in the cosmos. The history of science shows that the Drake equation has inspired generations of researchers. Many astronomers admit it was what drew them into their careers. It became a symbol of scientific optimism. We can take a question that seems infinitely complex and turn it into concrete steps. The cultural influence is vast. In literature and cinema, it has fueled stories of contact with alien civilizations. Films about humanity's future often echo themes of the search, themes rooted in Drake's ideas and those of his contemporaries. Even the absence of contact has become a cultural symbol, reflecting our doubts and fears. Think of it. The Drake equation is an example of how science becomes art. It gives rise not only to formulas but also to metaphors, paintings, and stories. It broadens the boundaries of imagination and inspires millions far beyond astronomy. Thus, the 13th chapter of our journey shows that the Drake equation lives not only in science, but in culture. It has become a bridge between rigorous astronomy and human dreams, and perhaps it is that bridge which will one day lead us to a great discovery. In the next chapter, we will speak of the future of research. What new tools and projects may help us approach the mystery of the Drake equation? In the previous chapter, we explored the cultural and philosophical influence of the Drake equation. Now it is time to look to the future. What new tools and projects may bring us closer to solving this great cosmic mystery? For science does not stand still, and each year opens new horizons. Let us begin with telescopes. In 2021, the James Webb Space Telescope was launched. Its sensitivity allows us to study the atmospheres of exoplanets dozens or hundreds of light years away. If oxygen, methane, or other biomarkers are detected, it would be a step toward understanding the probability of life. In the coming years, new giant ground-based observatories, the European Extremely Large Telescope and the 30-meter telescope, will join the quest. Another direction is the study of nearby planets and moons. Missions to Europa and Enceladus aim to test whether their icy shells hide oceans full of life. Mars expeditions continue to search for traces of an ancient biosphere. Each discovery expands our sense of how varied the conditions for life may be. SETI, too, is evolving. Modern projects employ artificial intelligence to analyze vast amounts of radio data. New initiatives explore optical telescopes and even gravitational wave detectors as tools for the search. The idea is simple. The more we open our eyes and ears, the greater the chance of hearing the cosmos. Philosophically, the future of research is tied to humanity's own development. The more sustainable our civilization, the more resources we can invest in the search. International cooperation may be the key. Projects on the scale of SETI or interplanetary missions require the combined efforts of dozens of nations. In this sense, the Drake equation functions not only as a formula but as a stimulus for unity. The history of science shows that every technological leap leads to new discoveries. Galileo's telescope transformed our vision of the solar system. The radio breakthroughs of the 20th century opened the universe to us. Perhaps the new instruments of the 21st century will lead to an answer to the question we have asked for centuries. Think of it. Right now, some telescope may be recording data that contain the signal of another civilization. We simply have not yet learned how to recognize it. Or within Martian rocks lies a microscopic trace of life, awaiting discovery. The future of research promises not only answers, but new questions. Thus, the 14th chapter of our story speaks of hope and expectation. We stand on the threshold of an era when the Drake equation may shift from philosophy to concrete scientific discoveries. In the next and final chapter, we will draw our conclusion and look at the Drake equation as an inspiring reminder of humanity's place in the universe. We have reached the final chapter of our journey through the Drake equation. Step by step, we have explored each factor, asking questions about stars, planets, life, intelligence, and civilizations. Now it is time to conclude and attempt to see the whole picture. The Drake equation does not yield a precise number. It does not predict the future, but it gives us something greater, a framework for thought. It transforms the abstract question, "Are we alone in the universe?" into a set of concrete problems we can investigate. How many stars form? How many have planets? How often does life arise? How long do civilizations endure? For each of these, we are gradually finding answers. Philosophically, the Drake equation is an invitation to both humility and hope. If civilizations are numerous, we are part of a vast cosmic community. If we are alone, then we bear a special responsibility to preserve and nurture intelligence in the universe. In either case, we find meaning and purpose. The history of science shows that the equation has been a powerful catalyst for exploration. It sparked SETI projects, space missions, new telescopes. It inspired generations of scientists and ordinary people alike. Even without a definitive answer, the very search has reshaped our vision of the cosmos. Think of it, once we believed Earth to be the center of creation. Then we learned it was just one planet. Then we discovered that planets number in the billions. Now we ask, how many of them harbor life and mind? This chain of questions and discoveries defines us as humanity, a species that seeks. The concluding thought is simple yet inspiring. Regardless of the number of civilizations, the universe grows larger and richer when we ask questions. The act of searching itself makes us part of the cosmos, and if someday we hear a signal or meet others, it will be the greatest event in history. But even if not, we have already found something essential, the ability to dream and to reach for the stars. Thus, the Drake equation is not merely a formula but a philosophy, a reminder that humanity is part of something vast. It calls us to knowledge, to unity, to hope. And perhaps that hope itself is the most important answer to the question, are we alone?